Boeing is a great example of an enterprise working to adopt quantum computing technology. We at IBM have a long working relationship with the Boeing quantum team led by Jay Lowell. Jay in particular has done a great job thinking about how to get quantum out of the research community and into the pipeline of their business. This kind of thinking is really important for success in the next decade of quantum computing.
We at Boeing are trying to assess how quantum computing applications fare today using state-of-the-art computing resources and objectively project that forward so we have a better understanding of what we are going to do in the future. There are two examples of our quantum computing application work that show what this looks like in practice. The first is looking for better epoxies that resist aging from too much exposure to the sun. We use paint-like epoxy coatings on many of our products. Over time, light from the sun can break the chemical bonds in the coatings, reducing their protective properties. It's very important that we understand how long it takes for this to happen so we can know when we need to reapply them. Today, we can get approximate answers to this question two ways: costly lab experiments or rough answers using classical computers alone. Both of these methods are imperfect. We think we can do better in the future. A near-term quantum computer can simulate much of this reaction today. We are doing that work now and using emerging state-of-the-art algorithmic methods called sample-based quantum diagonalization and generalized entanglement forging. We are pushing our problem scale as much as possible on today's quantum hardware. Our focus is understanding the limit of what we can do today and using that to project forward into the era of large-scale fault-tolerant quantum computing. This work shows us we are very near the point where we will begin integrating quantum computing into our workflows. And by doing this work, we are peering into the future where quantum computers solve expensive problems at scales impossible today. Another example of our work is investigating algorithms that can model how corrosion operates at the level of individual chemical reactions across large length and time scales. Fighting corrosion is an extremely high-value problem, worth $2.5 trillion per year globally. If we can model those reactions, we can search for more corrosion-resistant alloys. We now know the scale that quantum computers will need to be for us to do this work in practice, and we have a deep understanding of the algorithms and quantum classical workflows involved.
Boeing has built a quantum team that collaborates broadly across its organization, working with experts throughout the business to identify and tackle high-value problems of quantum computers. They are pushing the limits of what's possible today and readying themselves for what will be possible in the future, outlined by the IBM roadmap to large-scale fault-tolerant quantum computing. It's a model for any enterprise that wants to get a competitive edge from quantum computing.